You've seen what types of engine sensors are used in vehicles. Now let's look at how the simplest sensor circuits use switches. For example, when you step on the brake, the stop lamp circuit is completed, providing power to the stop lamps. This on-off signal is sent to other modules as well as the PCM. A temperature sensor is a variable resistor, or thermistor. Temperature sensors provide data such as coolant temperature, intake air temperature, cabin air temperature, and transmission oil temperature. As a rule of thumb, most thermistors have a very high resistance when the temperature is cold and low resistance when it is hot. This is called a negative temperature coefficient, or NTC, which is the opposite of a positive temperature coefficient, or PTC, the way most other electrical components function. Use the slider to view the relationship between temperature and resistance in a thermistor. A thermistor is wired in series from the PCM 5-volt supply with a return path to ground through the PCM. For the PCM to use a thermistor as an input, it has to be able to monitor the change in resistance value. To accomplish this, a fixed resistor is added in series with the thermistor. This resistor is inside the PCM and is sometimes called a dropping resistor. This is a series circuit with two loads. In a series circuit, voltage is shared by each load. The PCM monitors the circuit voltage between the fixed resistor and the thermistor. At the monitor point, the voltage varies depending on the resistance of the thermistor. When the thermistor is cold, it has very high resistance, so most of the voltage drops across it. As temperature increases, resistance decreases, and so does the voltage drop across the thermistor. You can expect to see this range of voltage change when you monitor a thermistor signal on the scan tool. Use the slider to see how this works. A heated O2 sensor, or HO2S, is also a type of variable voltage signal sensor. Most current vehicles use zirconium or wide-range linear oxygen sensors. Some earlier model vehicles used titanium oxide sensors. A binary oxygen sensor produces a voltage between 100 and 900 millivolts. The sensor must be hot to operate. Oxygen sensors have an integral heater to speed their warm-up on cold engine starts. The H in the abbreviation means heated oxygen sensor. The oxygen sensor is mounted in the exhaust gas stream. There's also a vent on the ambient air side of the sensor. The sensor reacts to the difference in oxygen levels between the outside air and the oxygen present in the exhaust gas. When the engine is running rich, there is almost no oxygen in the exhaust, so the difference between the oxygen level in the exhaust and the outside air is high. This results in a 700 to 900 millivolt output from the sensor. When the engine is running lean, there is oxygen present in the exhaust, so the difference between the exhaust gas and outside air oxygen levels is lower. This results in a 100 to 300 millivolt output from the sensor. Being aware of the differences in how oxygen sensors respond to the presence of oxygen in the exhaust stream is absolutely critical for accurate diagnosis and repair. Zirconium oxide sensors, ZrO2, use a zirconium oxide film to sense the oxygen content of the engine exhaust gas. They are installed upstream and downstream of the manifold catalyst converter. As the zirconium oxide sensor measures the oxygen content of the exhaust gas, it communicates with the ECM on a continuous basis. When the air-fuel ratio is rich, it generates approximately 1 volt, and when it is lean, it generates nearly 0 volts. Heated zirconium oxide sensors come up to temperature in less than 8 seconds, which assists in reducing emissions during cold start. The wideband oxygen sensor is a 5-wire sensor that reads oxygen content in much the same way as a traditional oxygen sensor. It uses a planar type construction with a special 2-part sensing element to measure how much oxygen is in the exhaust. Compared to a usual zirconium or titanium oxygen sensor, the wideband or wide-range linear oxygen sensor can measure the air-fuel ratio over a much wider range. This wide-range linear O2 sensor produces a voltage signal that corresponds to a specific air-fuel ratio. It has the ability to not only indicate if the mixture is rich or lean, but also how rich or lean. A lean mixture is indicated by a high voltage above 2.8 volts. A rich mixture is indicated by a low voltage below 1.8 volts when monitored in current data. The output signal of the wide-ranger linear O2 sensor is controlled by a variable current, positive or negative, while the output of the typical zirconium oxygen sensor is a variable voltage. The PCM constantly monitors the linear O2 sensor and increases or decreases the fuel injection duration based on this signal. Always check the service manual to determine expected voltage on a given circuit. A wide-range linear air-fuel ratio sensor operates in a different manner than a binary-type oxygen sensor. The PCM supplies a positive or negative current to the air-fuel ratio sensor's pump circuit, or IP, to maintain the air-fuel ratio at 14.7 to 1. When the air-fuel ratio is rich or lean, the circuit is no longer in balance and current travels through the circuit. When the system is rich, a negative current is supplied to maintain lambda, and when the system is lean, a positive current is supplied to maintain lambda at 1. Wide-range sensors are capable of providing a precise air-fuel ratio, ranging from 11 to 1 to 23 to 1 air-to-fuel ratio from the normal optimum stoichiometric ratio of 14.7 to 1. The power steering pressure transducer signals to the ECM the load sensed as steering input increases and steering hydraulic pressure also increases. The ECM performs the appropriate electric load corrections, controlling idle speed value. The power steering pressure switch signal is a voltage between 0 and 5 volts, which is proportional to power steering pressure. Low pressure produces a low voltage signal, and high pressure produces a high voltage signal. The knock sensor is very similar to a microphone. It detects the vibrations caused by pre-ignition and outputs a voltage signal to the ECM. The ECM then adjusts ignition timing to eliminate the pre-ignition condition. Under normal operation, based on knock sensor input, the ECM will advance ignition timing until pre-ignition occurs and then retards timing slightly to maintain knock-free operation. A malfunction of the knock sensor circuit can cause pre-ignition and engine-damaging detonation because the PCM won't know to retard the ignition timing when pre-ignition is occurring. At idle, the signal circuit should read less than 1 volt. If knock occurs, voltage approaches a maximum of about 4.5 volts. On an oscilloscope, you can see that the initial shock deforms the sensor and the piezo-resistive elements generate high voltage. As vibrations subside, voltage approaches 0. Piezo-resistive devices change resistance as pressure on their surface is applied and released. In this MAP sensor, a diaphragm is covered with piezo-resistive film. The PCM supplies 5-volt reference. As the diaphragm moves in response to atmosphere pressure changes, the resistance changes and voltage on the signal wire changes also. Potentiometers are typically used as voltage dividers. One outside lead is attached to ground and the other outside lead is attached to the power source. The two outside leads are internally connected with a resistive path. The center tap or signal circuit is attached to a movable slider or wiper arm that moves across the surface of the resistive path. As the center tap moves along the path between the ground side and the 5-volt side, the center tap voltage varies from 0 to 5 volts. A throttle position sensor is a variable resistor potentiometer. Here's a closer look at how it works. The wiper picks up the variable voltage on the resistance wire and sends it to the ECM-PCM with the reference signal voltage dropping across the resistance wire. That means the voltage is very close to 5 volts near the reference signal input and very close to 0 volts at the sensor ground. This is voltage range you would expect to see when monitoring sensor operation on the scan tool. Use the slider to view sensor operation. Many automotive circuits include a feedback circuit so you can verify proper operation. For example, the temperature door in the HVAC unit is able to provide the climate control system module with feedback about the position of the temperature door. The module can compare the commanded position of the door with the actual position of the door. The module will provide power to the motor until the feedback circuit indicates the requested position has been achieved. You can view the feedback circuit voltage or status on the scan tool. Note that this type of feedback circuit is virtually identical to the throttle position sensor circuit. The fuel level sensor is a variable resistor circuit. Note, this is a 2-wire circuit, not a 3-wire with a fixed reference voltage. This circuit uses an input voltage of 5 volts with a variable resistor to ground. As the fuel level changes, the voltage change indicates the fuel level to the cluster and the PCM. Fuel level is monitored by the ECM to determine the amount of gas left in the tank. It is also used by the evaporative system to confirm the fuel level is within 15 to 85% for the purpose of running the EVAP test. Variable reluctance AC sensors are electromagnetic devices consisting of a permanent magnet surrounded by a coil winding to generate an alternating current. As the notches or teeth of the ferrous reluctor wheel rotate past the tip of the sensor changes the magnetic field, creating an analog voltage signal in the sensor coil. The crankshaft position sensor, or CKP, measures the engine RPM. It also may detect when the cylinder is on the power stroke. Similarly, the camshaft position sensor, or CMP, indicates camshaft position for use in valve timing. One type of wheel speed sensor generates AC signals and indicates vehicle speed. The control module uses changes in the signal to determine position or speed. Pulsed signals can be read on a digital multimeter, however voltages are averaged between the highest and lowest signals. Because of this, these types of signals should be checked on an oscilloscope. A Hall effect sensor uses a reluctor or shuttle wheel passing through a magnetic field detection device. Typically, the sensor is integrated with a wound core or permanent magnet that surrounds the conductor. When the tooth passes through the magnetic field, the signal is on, and when a gap is present, the signal is off. The device outputs a digital signal. You can view this signal on an oscilloscope as shown here. The crankshaft position sensor, or CKPS, is a Hall effect type sensor that generates a voltage using a Hall sensor and a target wheel mounted on the crankshaft. There are 58 slots in the target wheel, with one slot longer than the others. When a slot in the wheel aligns with the sensor outputs a low voltage. When a metal tooth in the target wheel aligns with the sensor detects a magnetic field and outputs a high voltage. During one crankshaft rotation, there are 58 regular signals and one longer signal. The PCM calculates engine RPM by using the sensor's signal and controls the injection duration and the ignition timing. Using the signal differences caused by the longer slot, the PCM identifies which cylinder is at top dead center. Hall effect sensors are used for some wheel speed sensors, where most have used an AC signal, and vehicle speed sensors have been a conventional type with 3 wires. This type of wheel speed sensor only uses 2 wires with a feed voltage of 12 volts with the ground as the signal wire. Conventional Hall effect wheel speed sensors generate a square wave signal with a frequency proportional to the speed of the vehicle. The ECM and ESC modules use the WSS signal to determine the vehicle's speed. The ECM uses information from the wheel speed sensor to control fuel injection, ignition timing, transaxle shift scheduling, and torque converter clutch scheduling. The WSS signal is also used to detect rough road conditions. The wheel speed sensor, shown here, uses two Hall effect sensor elements, A and B. Element A produces a sine wave signal that reflects changes in the magnetic field as it passes over each gear tooth on the wheel. Element B also produces an opposite sine wave signal that reflects changes in the magnetic field as it passes over each gear tooth on the wheel. Some current vehicles use a mass airflow sensor that directs incoming air across a heated wire. 12 volts is applied to heat the wire. The resistance of the wire decreases as heat is drawn away by the air traveling across it. The MAF sensor measures the voltage drop across the wire, and an internal amplifier outputs a varying frequency that the ECM uses to calculate the mass of the air entering the engine throttle body. An internal thermistor in the MAF sensor compensates for incoming air temperature. This sensor self-cleans the wire at the end of each driving cycle by heating it to burn off any accumulated dirt or debris. Most MAF sensors flow at approximately 3 to 5 grams per second at idle and 65 to 85 grams per second at maximum engine load.